So now in chapter 4.2, we're going to be looking at logarithmic functions. So in 4.1, we were looking at exponential, so now we're moving on to logarithmic. So remember from previously, hopefully you can remember some of this, inverse functions can be found by interchanging the x's and the y's and then solving it for y. So let's say we had an exponential, and it was y equals b to the x. So y is a function, x is the variable, b is the base. What we would do is we interchange the x and the y, and then we would solve for y. So when we interchange the x and the y here, we're going to end up getting x equals b to the y, and then we try to solve for y. So when we're trying to solve this for y, we up until this point didn't really have anything that would isolate that y. We can't like divide both sides by b or add b to both sides or anything to solve for y. So what we actually have to do, this is where the logarithms come into play. When we solve for y, we end up getting y equals log base b of x. And this is the inverse function of y equals b to the x. So we already knew that exponential functions y equals b to the x, they were one-to-one functions, meaning they have an inverse function, and the logarithmic function is the inverse function of the exponential functions. So the inverse of an exponential with base b is the logarithmic function with the same base b. So I'm just going to write down how we read this off because it is important. So it's log base b of x. B is the base, it's a subscript here, and then x is the input. So here's a definition we'll be using for a logarithmic function. If we have something that's b to the y equals x, that's the same thing as y equals log base b of x. So this over here is exponential form. And on the right-hand side, it is logarithmic form. So technically also here, b has to be positive, and b cannot equal 1. So for exponential functions, the base is positive, and b cannot be 1, because if we had 1 raised up to any power, it would just equal 1 for every exponent, and that would not be exponential. So same thing for logarithms, though, b has to be positive, and it cannot be equal to 1. So if you notice here, a logarithm is essentially an exponent. If we have b to the y equals x in exponential form like we do on the left, we can see that the exponent of the exponential form is y. On the right-hand side, we can see that y equals log base b of x, which is the exponent. So in a sense, a logarithm is just an exponent. So let's do some examples for converting. So for the first one, we want to convert from logarithmic form to exponential form. So I'm just going to rewrite that rule right here. B to the y equals x is the same thing as y equals log base b of x. Okay, first one we have 2 equals log base 5 of x. So we want to convert this into exponential form. So one way you can do this, you can identify the y, identify the b, identify the x, and then put it into its appropriate exponential form. So we have base 5. I like to go right to the base. It's base 5 raised up to the 2, and that's going to equal the x. So this is the same thing as 5 to the second equals x. And I'm just going to leave it like that because that's exponential form. I'm not going to evaluate 5 squared. Okay, next one we have 3 equals log base b of 64. So once again, I like to start with the base. It's base b. Then you go to the other side of the equation. It's b to the third equals 64. So b cubed equals 64. And for the last one here, log base 3 of 7 equals y. Start with the base, raise it to the other side of the equation, equals the input, so 7. So 3 to the y equals 7. So if you have to write down the conversion, write it down and identify y, b, and x, or just do it the way that I was kind of saying it out loud there. So let's write each equation in logarithmic form now. So we're starting with exponential form and we want to write it in logarithmic form. So I'm just going to write the conversion right here again. So we have 12 to the second equals x. So this is going to be the exponent equals log base 12 of x. So for logs, it's always the exponent equals log base, whatever the base of the exponential is, same base of the other side of the equation. Next, we have b to the third equals 8. So it's going to be the exponent equals log base b of 8. Lastly, e to the y equals 9. So remember, e is the natural base. It's about 2.718. So this is going to be the exponent equals log base e of 9. So it's just a number, so don't let that screw with you at all. Log base e, that'll pop up again later, I believe, at the end of this section, but I'll mention that when we get there. Okay, so let's work on evaluating these by converting them into exponential form. There's going to be multiple ways that we actually can evaluate logarithms when the base is a number and the input's a number. One way is obviously this way, so let's convert these to exponential form. For a, we have log base 2 of 16, so converting this to exponential form, it's going to be, what we're going to need to do here is kind of pull a little bit of a trick. We're going to say this is equal to x. We're going to say it's equal to something, and we're trying to figure out what that something is. So converting this to exponential form, it's going to be 2 raised up to the other side of the equation equals 16. So we have to think about what would x have to be here. 2 to the what equals 16. That means x has to be 4 because 2 to the 4th power equals 16. So that means log base 2 of 16 equals 4. So let's do the same thing for the next one. Log base 7 of 1 over 49. Let's set that equal to x, and we're going to be solving for x. So this is going to be base 7 to the other side, which is x, equals 1 over 49. So we have to think, what does x have to be here in order for this to be true? So clearly this got reciprocated, right? The 7 became 1 over 49. So that means x is going to be negative something. 7 squared equals 49. So that means x is going to be negative 2. 7 to the negative 2 equals 1 over 49. So that means log base 7 of 1 over 49 equals negative 2. So we have log base 25 of 5. So converting, or setting it equal to x again, setting it equal to something. Converting it into exponential form, that's going to be 25 to the x equals 5. So trying to think of what x has to equal here. 25 to what power equals 5? We know that the square root of 25 equals 5. That is an exponent of 1/2, so x has to equal 1/2 here. So log base 25 of 5 equals 1/2. And for last one here for D, log base 3 of 27, set it equal to x, convert it to exponential form. That's going to be 3 to the x equals 27. So we think, what do we have to raise 3 to in order to get it to 27? The answer is 3, because 3 cubed equals 27. So that means log base 3 of 27 equals 3. So just a quick little sidetrack here going up to the top. Logarithm is a pretty weird word, as I'm sure you already noticed. The origin for it comes from logos and arithmos, so it's Greek. Logos means ratio. Arithmos is number. So it's literally a ratio number. What that's kind of saying is that it is an exponent. It's telling you what the base is being raised to. It's telling us how many times we're multiplying a number by itself. So that's kind of the reasoning for its name. But it just kind of came to my head real quick randomly, so I figured I would mention it. Okay, for the next thing, just some properties involving the number 1. So here are the two main properties involving 1. The first one is if we have log base b of that same b, it's always going to equal 1. So if we have, so the base and the input are the same, it's always going to equal 1. So converting this into exponential form, say because if we put this into exponential form, this would be b to the first power equals b, which we obviously know is true, right? Because b to the first power, it's just b. So that kind of hopefully makes more sense in exponential form. For the next one, if we have log base b of 1, that will always equal 0. So log base anything of 1 is going to equal 0. Converting this into exponential form, this would be b to the 0 equals 1, which once again, hopefully we know that that's true because anything to the 0 power equals 1. So let's evaluate these, keeping those in mind. So if we have log base 7 of 7, so the base and the input are the same, that's going to equal 1. Next one, log base 5 of 1. Log base anything of 1 equals 0. Log base, for next one, log base 1/2 of 1/2. So this is the first time, well, maybe not the first time, or I don't remember if it is the first time, that we have a fraction as the base, which is okay. Log base 1/2 of 1/2 is going to be 1 because it's the same base and the same input. And then log base 10 of 1 equals 0 because log base anything of 1 equals 0. Okay, so easy enough, but just keep those in mind. Okay, so moving on to the next thing here are the inverse properties. So not as easy as what we just did with the properties involving ones. So if we have the function, the exponential function f of x equals b to the x, then that means f inverse is log base b of x. So remember the -1 exponent, it's not an exponent, it's a superscript and it represents the inverse. So that's just saying b to the x and log base b of x are inverses, which we already discussed. So what that means, if you remember back to inverse properties of functions, f of f inverse of x equals x, and f inverse of f of x also equals x. So when you take an inverse function as the input to the function, essentially everything cancels except for the x. So what this means is that b raised up, instead of b to the x, b raised up to the log base b of x just equals x. And instead of log base b of x, log base b of the exponential b to the x, that also equals x. So those are the exponential, or the inverse properties of the logs. So let's use those properties to evaluate these. So we have, for the first one, log base 4 of 4 to the 5th. So what we could do here is we could evaluate 4 to the 5th. I don't even know what that is off the top of my head. And then say log base 4 of whatever that is equals x. We can convert it to exponential form and try to figure out what the exponent is again, like we've been doing. Or we can recognize that those are inverses. We have log base 4 of an exponential that is also base 4. So they're going to cancel, and it's just going to equal the exponent, which is 5. For the next one, we have 6 raised to the log base 6 of 9. So the exponential is base 6. And the log inside of the exponential is also base 6, so they're going to cancel. And this is just going to equal 9. Next one, log base 10 of 10 to the negative 2. So the log is base 10, so is the exponential in the input. They're going to cancel, and we're left with negative 2. Next, we have log base 3 of 3 to the 8th. Base 3's cancel, and we get 8. 10 raised up to the log base 10 of 4. They're both base 10. They cancel. We're just left with 4. And lastly, we have 5 raised up to the log base 5 of 1. Okay, so for this one, using the properties that we actually just are doing right now, the inverse properties, they're both base 5, the exponential and the log. So it's just going to cancel to 1. Or what we can recognize here, if we wanted to, is that 5 raised up to the log base 5 of 1. Log base 5 of 1 equals 0, right? Based on the properties that we just did a second ago. Log base anything of 1 is 0. So this is 5 to the 0, which is also 1. So whichever way you want to think of it, either way it's correct. Okay, so kind of jumping back a little bit, another way for us to think about converting between logarithmic and exponential form. This is the way that I'm doing it, kind of when I'm doing this stuff. So I at least wanted to mention it. It's technically nothing new, but it's just an extra way to think of it. So let's say we're starting with logarithmic form here. Let's say we have x equals log base b of y. And we try to put this into exponential form. So hopefully by now you can maybe figure out, if you think about it for a second, you know this is going to be b to the x equals y in exponential form. What we can do here though is we can base b both sides. And then let's see what happens when we do this. So what this means is essentially we're taking both sides of the equation here to be exponents on base b. So it's going to be b to the x equals b to the log base b of y. So our original expressions on both sides of the equation are now exponents to base b. The left-hand side stays the same. It's just b to the x. The right-hand side, we're actually using the inverse property here. B raised up to the log base b of y. They're both base b, same bases. They cancel. We're just left with y. So that gives us our exponential form. Okay, and then for the next thing, now converting from exponential to logarithmic. So starting with b to the x equals y this time. Once again, you can just use the definition, use that conversion, and say that's going to be x equals log base b of y. Or you can do it this way. Once you start with this, you can log base b both sides. So what that means is we're going to have log base b of b to the x on the left, and then log base b of y on the right. Log base b of b to the x, that's the inverse property from the previous page. Both base b, they cancel. We get x equals log base b of y. So that's the, now it's in logarithmic form here. So you don't have to think about it this way. I'm going to do a couple examples though, using it this way. All right, so let's solve for x here. So once again, if you don't like the way I just mentioned, then just use the way that you were doing previously. So we have 4 equals log base 2 of x. So solving this for x, let's convert it into exponential form to see what happens. So what I'm going to do is I'm going to base 2 both sides. So all I'm doing is putting it into exponential form. So if you base 2 both sides, you're going to end up getting 2 to the 4th equals 2 to the log base 2 of x. 2 to the 4th is going to equal, so 2 to the log base 2 of x, they're both base 2, they cancel, we get x. 2 to the 4th is 16, so we get x equals 16. Okay, next one we have log base 3 of x equals 2. So log base 3 of x equals 2. So putting this into exponential form here, it's going to be 3 to the second equals x. So base 3 to the second equals x. So this is going to give us x equals 9. So I just kind of skipped doing that intermediate step of converting it into exponential form. Next one, log base 9 of x equals 2. So once again, I'm going to skip that intermediate step of putting it into that form. It's going to be 9 to the second equals x for exponential. So this is going to be x equals 81 for 9 squared. And next one, 4 equals log base x of 16. So it's going to be x to the fourth equals 16 in exponential form. So we have to think what raised up to the fourth power is going to give us 16. So it has to be 2. 2 to the fourth equals 16. So that time we were solving for the base. Okay, let's make them a little bit harder here. We'll be getting into harder ones in several sections. Log base 3 of x minus 1 equals 2. So it's the same concept. It's going to be base 3 squared equals x minus 1. Obviously looks a little different only because the input is x minus 1. It's a binomial this time, which is fine. So this is going to be 9 equals x minus 1. So linear equation, we have to add 1 to both sides, so we get x equals 10. So 9 plus 1 is 10, cancels with the x minus 1 on the right. Okay, and for the last one here, before we get into the graphs, we have log base 5 of x plus 4 equals 3. Putting this into exponential form, it's going to be base 5 to the third power equals x plus 4. So that's 125 equals x plus 4. Subtract 4 on both sides, we get x equals 121. Okay, so that was still just converting from logarithmic to exponential form, but solving for a given value of x there. So getting into the graphs of logarithmic functions, the graph of the function f of x equals log base b of x is going to be the graph of g of x equals b to the x. So it's going to be the graph of the exponential with the same base, reflected over the line y equals x. The reasoning is because they're inverses. So if you remember, inverse functions are, graphically speaking, are reflections of each other over the line y equals x. So let's graph f of x, which is 2 to the x, and g of x, which is log base 2 of x on the same set of axes to see what that looks like. So I set up these tables. So for this first table here, for 2 to the x for the exponential, I'm going to plug in some values. I'm going to plug in -2, -1, 0, 1, and 2. So if we plug that in, 2 to the -2 is 1 over 2 to the positive 2, which is 1/4. 2 to the -1 is 1 over 2 to the positive 1, so 1/2. 2 to the 0 is 1, 2 to the first is 2, and 2 to the second is 4. So we could, for this next table on the right, so I'm going to plot these points in a second. On the next table on the right, we could plug in values for x. It's a little bit more annoying, though, plugging in these values, because then we would have to think, okay, what's log base 2 of whatever? We might have to convert to exponential form to help us. You'll see later on that we can use our calculator using this other method. What I'm going to do here is use this definition of inverse functions to help us. Inverse functions, if the coordinate x comma y is a point for the function f of x, then on its inverse function, that's going to contain the point y comma x. So what that means is you interchange the x and the y coordinates. So that's what I'm going to do for this. I'm going to interchange the x and the y's. So the first one, instead of -2 comma 1/4, it's 1/4 comma -2. Instead of -1 comma 1/2, it's 1/2 comma -1. And then 1 comma 0, 2 comma 1, and 4 comma 2. So it's a nice little shortcut that you can use because they're inverses, because one's a logarithm, the other's an exponential, and they're both base 2. So let's graph these and see what it looks like here. So I'm going to graph the exponential first. So negative 2 comma 1/4, negative 1 1/2, 0 comma 1, 1 comma 2, and 2 comma 4. So that's going to look like that exponential right here. So that's f of x equals 2 to the x. So before I graph this next one, the line y equals x, we know that it looks like this. So y-intercept of 0, slope of 1. So we know that the logarithmic function that we're about to graph is going to be a mirror image of that exponential over that line. So let's plot these points down. So 1/4 comma negative 2 for the exponential here. So that's going to be about right here. And then it was 1/2 comma negative 1. And then 1 comma 0. 2 comma 1. And 4 comma 2. So connecting these points, we can see it's going to look something like this. So this is g of x, which is log base 2 of x. So you can see that it's a mirror image of its inverse exponential function over that line y equals x. You can see that it's still increasing, but it's increasing at a much slower rate. And you can probably tell that there's going to be a vertical asymptote at x equals 0. And that's because the exponential had a horizontal asymptote at y equals 0. Okay, so that is the graph of what a log will look like. So let's see some more generic properties here. So we kind of have two options here, just like we did with exponentials in terms of their bases for what they look like. We have either the base is greater than 1 or the base is between 0 and 1. So the base is going to be positive and it's not going to be equal to 1. So if the base is positive, it's going to look like this graph over here on the left. So if it's positive, it looks exactly like what we just did. So it kind of helps to know these 2 points that are labeled on both of them. The x-intercept is going to be at 1. Because if we plug in x equals 1, log base b of 1 equals 0, because log base anything of 1 equals 0. So that's going to be the x-intercept. And we also know the point b comma 1 is going to be on the graph, because log base b of b equals 1. Okay, for the next one, for base being between 0 and 1, for this one on the right. So the base is between 0 and 1, so something like 1/2. It's going to be decreasing. So notice for both of these graphs, there's a vertical asymptote at x equals 0. So this one is going to be a decreasing function. The point b comma 1 is still on the graph, and it still has a x-intercept of 1. So here are some of the important properties right here. If the logarithmic function is in the form f of x equals log base b of x, then all of these properties hold. The domain would be 0 to infinity, and the range would be negative infinity to infinity. So notice that this is the complete opposite of the exponential function. Once again, that's because they're inverses. So inverse functions have flip-flopped domain and ranges. Okay, then the x-intercept for these is going to be at the point 1 comma 0. There is no y-intercept. That's because there is a vertical asymptote. There is a vertical asymptote at x equals 0, which is the y-axis. And if the base is greater than 1, it is going to be increasing. If it's between 0 and 1, it is decreasing. Okay, so moving on to transformations. So we'll still be graphing it, but we're going to be maybe do maybe 2 examples with transformations. So for transformations, same transformations that we've done in the past. So we're doing these on the form log base b of x. So starting with a vertical shift, we know it has a vertical shift if it's log base b of x plus or minus c completely after the fact. If it's plus c, that means we're moving log base b of x up c units. If it's minus c, we're moving it down c units. For the horizontal shift, if it's log base b of x plus c or x minus c in those parentheses, so the plus or minus c is attached to the x. Plus c means it's to the left, so remember that's the opposite of what you would think. To the left c units, minus c is to the right c units. For reflections are when we're negating things, negating the x or the y. If we have a -1 multiplying out front, negative log base b of x, that means it's going to be a reflection over the x-axis. If we have a negative multiplying the x, that's a reflection over the y-axis. And for vertical stretching or shrinking, if we have a number, so c in this case, multiplying out front, c times log base b of x, that's going to be a vertical stretch or shrink. It's going to be a vertical stretch if the c value is greater than 1. It's going to be a vertical shrink if c is between 0 and 1. So stretch meaning it's moving away from the x-axis, shrink meaning it's moving towards the x-axis. Lastly, horizontal stretch and shrink. That's when we have a number c, in this case, multiplying the x, and it's the opposite of what you would think. If c is greater than 1, then it's actually a shrink. If it's between 0 and 1, it is a stretch. So a shrink, meaning it's moving towards the y-axis, a stretch, meaning it's moving away from the y-axis. Let's do 2 examples of transformations. So we're going to graph g of x, which is 3 plus log base 4 of x minus 1, using f of x, which is log base 4 of x. So as usual, I'm going to start with this basic function, which is given to us. The basic function is just log base 4 of x. So we should know what the shape looks like for this based on what we just did. We know there's going to be a vertical asymptote here at x equals 0. And we know it's going to be increasing because the base b is 4. It's greater than 1. So I'm going to come up with just a really small table for x, y values. I'm going to plug in a 1 and I'm going to plug in a 4. So I did this on purpose because log base 4 of 1 equals 0, the x-intercept, and log base 4 of 4 equals 1. So graphing that, we get 1, 0 and 4, 1. And then we should, once again, just know the shape looks something like this. So something like that, and this is the function f of x equals log base 4 of x. So now we have to apply the transformations in the proper order to find g of x. So the first thing that we always have to check is for a horizontal shift. There is a horizontal shift here. The x minus 1 is the horizontal shift. That means we're moving to the right 1 unit. So we're going to take all of these points and move them to the right 1 unit from the previous graph. That actually means the vertical asymptote is also going to move. So now the vertical asymptote's at x equals 1. Move that one to the right. And we move every other point to the right, and we end up getting something like this. And this is going to be, I'm just going to call it y. Y equals log base 4 of x minus 1. And the last thing here is that plus 3. So the plus 3 is a vertical shift. So normally, remember, we would check for reflections next. Or sorry, we would check for, so horizontal shift first, stretching and shrinking next, reflections third, and vertical shifts fourth. There are neither reflections or stretching or shrinking, so we go right to the vertical shift. And for the vertical shift, it's that plus 3, so that means we're going up 3. So we're going to move everything up 3 units. The vertical asymptote's not going to move because that doesn't move for moving up. And we're moving those 2 points from the previous graph up 3 units. So we're going to get something like, I believe something like this. And connect them, and we get our g of x, which is 3 plus log base 4 of x minus 1. Okay, so on to the next one here. So we have g of x. We're going to graph g of x, which is negative log base 2 of x plus 2, using our basic function f of x equals log base 2 of x. So starting with that basic function, once again, we should know the shape. The b is greater than 1 here. So I'm going to use a couple more points. I'm going to plug in a 1 and I'm going to plug in a 2. Because log base 2 of 1 equals 0, log base 2 of 2 equals 1. So plotting those points, we get this. We have the vertical asymptote at x equals 0 once again. Connecting these points gives us something like that. This is f of x, which is log base 2 of x. Okay, so next we check for a horizontal shift. There is no horizontal shift here. That x plus 2, the plus 2 is after the fact. It's not with the x, so that's actually a vertical shift. So next we would check for a stretch or a shrink. There is no stretching or shrinking. Next we look for a reflection. There is a reflection. There is negative out front. It's negating out front, so that means it's a reflection over the x-axis. It's negating the y values, the function values, so it reflects over the x-axis. So once again, our vertical asymptote stays put. We're going to reflect all of those points over the x-axis. This point stays the same for the x-intercept. The other point gets reflected to be over here, 2 comma negative 1. Essentially, we're just negating all of the y values. Connect those dots. And we'll get something like this. So this is y equals negative log base 2 of x. And lastly, actually, we check for a vertical shift. There is a vertical shift. We have the plus 2. So for this last graph down here, our final answer, it's going to be the vertical shift, which is everything gets moved up 2 units. So we go to that previous graph and we move everything up 2 units. The vertical asymptote is going to stay the same. So still a vertical asymptote at x equals 0. And moving all of those points up 2 units, we end up getting those 2 points right here and connecting them. We get something like that, and that is our function g of x, which is negative log base 2 of x plus 2. Okay, so that is all I'll do for transformations. So moving on to the domain of a logarithmic function. So recall from several pages ago, the domain of a logarithmic function, when it's in the form log base b of x, the domain is 0 to infinity. So if we looked at this graphically, we know that log base b of x has a vertical asymptote at x equals 0, and the graph would look something like this. Oops. So I'll say something like this, depending on what b is, but in general, same shape. So what that means is this x value right here, log base b of the x, the domain is when x is greater than 0, right? So that's the same thing as when the domain being 0 to infinity. So in general, it won't always obviously be log base b of just x. So in general, if we have the function log base b of something else, so I'll put log base b of g of x, where g of x is just another expression with x in it. The domain is going to be all the x values as long as g of x is positive. Okay, so let's take a look at some of these examples here. So finding the domain of the following. So the first one, f of x equals log base 4 of x plus 3. So to find the domain, what we are looking at is this input right here. So logarithms cannot take on negative values for inputs. So what we have to do is we have to say, okay, x plus 3 has to be greater than 0. So it can't take on negative or 0, a value of 0. So it has to be greater than 0. And then we isolate x. So subtract 3 on both sides, and we get x is greater than negative 3. So that's actually all we had to do. So the domain, I'm going to write this in interval notation, is negative 3 to infinity. So graphically speaking, if we graph this, this would actually look something like this. So we have a vertical asymptote here at x equals negative 3. And it would look something like this. Something like that. So you could see that it exists for x values that are greater than negative 3. Next one, g of x is log base 3 of 5 minus x. So once again, we're going to take this 5 minus x and say that is always going to have to be positive. Isolate x, so we would add x on both sides and get 5 greater than x. We don't really want to write it like that. That looks kind of silly. So we flip it and make it x less than 5. So the domain for this one is going to be negative infinity to 5. And if we ended up graphing this one would actually end up having a vertical asymptote at x equals 5. And it will look, there is a reflection in here, so it's going to look a little bit different. It would look something like this. So this would be g of x. And you could see that it exists for x values that are all less than 5. So let's make it a little bit harder here. F of x equals log base 2 of x minus 3 squared. So we are going to take the x minus 3 squared, and we are going to say that this has to be greater than 0. So the other two that we just solved, those ended up being linear inequalities. This is not a linear inequality, so we do have to be careful with this one. So when we're solving this, what we would do is we would take the square root of both sides here, right? And we would get x minus 3 is greater than plus or minus the square root of 0. If we solve this for x, we would get x is greater than 3. So it probably seems all well and good, and it probably seems like that's correct. We're actually missing another interval here. So what I'm going to do here is I'm actually going to erase this, and I'm going to pretend like this is an equal sign. So anytime that it is squared, you should do this method. So if that is an equal sign, then we would square root both sides, get x minus 3 equals 0. Add 3, we would get x equals 3. What I'm going to do is I'm going to set up a little number line. We know that x cannot equal 3 because that would make the input 0. We can't have an input of 0 for a log. So I'm going to come up with like a couple little test points here. I'm going to plug in 4 into this little expression. So test x equals 4, and I'm testing it to make sure that it's positive so that we know that it's part of the interval. So it's going to be 4 minus 3 squared. So this is going to equal 1 squared, which is equal to 1, which is positive. So I'm going to put a little positive here. And then I'm going to test something to the left of 3. So 4 was to the right of 3. I'm going to test something to the left, which would be something like 2. You could plug in a 1 if you want also, it doesn't matter. So plugging in a 2, 2 minus 3 squared, that equals negative 1 squared, which is actually positive 1, which is also positive. So that is also positive. So when I had this set up, we got x is greater than 3. The other part of the domain that we would have been missing is x is less than 3. It's because of that squared, because anything x minus 3, even when it's negative, when we square it, it's going to end up making it positive. So what I'm going to do is I'm going to say for the domain here, x minus 3 squared is greater than 0 for x greater than 3 and x less than 3. So I just, earlier when I had it set equal to 0 instead right above this, it's just so I can find that cutoff point because I knew we had to omit 3. So I'll put here, it's also that second interval of x less than 3 because of the squared. So the domain, the actual answer here is going to be, it's going to be negative infinity to positive 3, union 3 to infinity. So what that means is it's just everything except for 3. So if we were to graph this, there's actually a vertical asymptote at 3. X equals 3. This would actually look something like this. So it would actually be on both sides of that asymptote, which is something that we haven't seen up to this point. But the squared, the fact that there's a squared there, that's what makes this happen. So anytime you have something in this form where the input is something squared, a linear binomial in this case squared, all you have to do is recognize that the squared will make the negative portion positive after you square it, so it will also be part of the domain. So a little bit confusing for those ones. So for the last couple pages here, just introducing the common logarithm and the natural logarithm. So the common logarithm is just a logarithm, but it has base 10. So it's going to be f of x equals log base 10 of x. So we call it the common logarithm because we're in a base 10 number system, the decimal system. So we call it the common log. It tends to pop up a lot. Since it is so common, the way that we can write it is just log of x. We do not need to write the base in when it is base 10. It's understood that we're referring to log base 10. Okay, so this is going to be log base 10 for a couple properties. And the inverse, it is going to be the inverse of, I'll call it g of x, I guess, of g of x equals 10 to the x. So it's the inverse of an exponential because it's a log. It's base 10, so the inverse is 10 to the x. So that's the common logarithm. For the natural logarithm is going to be log with base e, just like the natural base, because it is the natural base e. So this is going to be f of x equals log base e of x. So we're not going to write like this. What we're going to write ln for natural log, but kind of reversed here, natural log of x. So it kind of just looks like ln x, but it's understood that it's the natural log of x. So just like I'm reading this right now, you read this as, you can either read it as ln, so that just, I guess, means ln, like you're reading the letters off, ln of x, or you read it as the natural log of x. Okay, so you pretty much should always be using the ln instead of log base e, but they mean exactly the same thing. So this is going to be log base e, and this is going to be the inverse of g of x equals e to the x. Okay, so these ones are really, really important. They pop up a lot. So if you see ln of x, you know that it's base e. If you see log of x, you know it's base 10. And since these are just normal logarithms, they have the same exact properties as the other logs. So let's kind of jump back here and go to converting between exponential form and logarithmic form, but using these different bases. So I'm going to write down the conversions back here on this page. So for the common log, converting between logarithmic and exponential form, that means 10 to the y equals x in exponential form is going to be the same as y equals log of x. So it's y equals log base 10 of x, but we don't have to write the base 10. For the natural log, that means that if we have something as e to the y equals x, base e, that's the same as y equals the ln of x. Y equals log base e of x. Okay, so I'm going to rewrite those right here just so you can kind of look back at it if you're following along. So e to the y equals x is the same as y equals ln of x, and 10 to the y equals x is the same as y equals log base 10 of log of x. Don't need the base 10. So doing this first example, ln of x equals 2. What this would be is x, putting this into exponential form, equals e to the second. So once again, you can use that conversion that I wrote down to help you. What I would do here is I would base e both sides and say e raised up to the ln of x equals x. And then e to the second is e squared, so you get x equals e squared. Next one, we have x equals ln of y. So that's going to be e to the x equals y. Now we have base 10. Log of x equals negative 10. So no base is written, so it's base 10. So it's going to be x equals 10 to the negative 10. So base 10. Next one is also base 10. Y equals log of z. So it's base 10, so it's going to be 10 to the y equals z. Okay, so let's go over the other way. So e cubed equals y. So it's going to be the exponent equals something. So this is base e, so it's going to be the natural log, and it's going to be the natural log of y. So 3 equals ln of y. Next one, 10 to the x equals 17. So this is going to be the exponent equals something once again. And it's going to be log base 10, because it's base 10, of 17. So we didn't have to write the base because it was base 10. And then e to the z equals 10. So it's going to be the exponent. It's base e, so equals the natural log of 10. Last one, we have y equals 10 to the negative 2. So it's going to be the exponent equals log base 10, so just log of y. Okay, so that is just extra examples using the common base and the natural base. So here are some extra problems here. I put several of them in here to make sure we're comfortable with all of this. So we're like 12 of these. So the first one is log of 100. So we're just evaluating or simplifying as far as we can go. So log of 100. So 100 is 10 raised up to something, right? It is a power of 10. We can rewrite 100 as 10 squared. The reason I did this is because this is base 10. It's not written, so we know it's base 10. Log base 10 of 10 squared. This is the inverse property. It's the same base on the log as well as the exponent and the input. So they cancel, and we're just left with 2. So you could have also set it up like this if you wanted and said log of 100 equals x, which means 100 equals 10 to the x. So x has to equal 2. Weighs a little bit longer though. Next one, log of 1000. Once again, this is base 10 because it's not written. So we could write this as log of 10 cubed. Inverse property, once again, base 10s cancel, we're left with 3. Or you could do it the way that I just wrote it out over on the right. Next one, log of 10 to the 7th. The base 10s cancel, so this is actually just 7. So all three of those first ones were kind of similar. Next one, we have ln of 1. So remember, log base anything of 1 equals 0. Next one, we have ln of e to the 6th. So ln is base e. Our input is also base e for the exponential. Inverse property, they cancel, and we get 6. Next one, ln of 1 over e to the fourth. So I see an e in here for the input, so I'm going to play with it a little bit. Instead of 1 over e to the fourth, we can write that as e to the negative fourth, right? Just based on exponent rules. The reason I did that is because now we can see that log, the ln is base e, so is the exponential in the input. They cancel, we're left with negative 4. Okay, and then for next one, we have e raised up to the ln of 5x. So the exponential is base e, and in the exponent is also base e with the ln. So they cancel, and we're left with 5x. Next, we have 10 raised up to the log of the square root of x. So it's base 10 exponential. The log in the exponent is also base 10 because it's not written. They cancel, and we're left with the square root of x. Next one, log base 3 of log base 7 of 7. So this one we're going to work kind of inside out here. We're going to work in the parentheses first. So it's going to be the log base 3 of something. The log base 7 of 7, that equals 1, right? Log base b of that same b always equals 1. So this is log base 3 of 1. Log base anything of 1 equals 0. Next one, log base 5 of log base 2 of 32. So once again, let's do this inside first in parentheses. So if I'm looking at this, log base 2 of 32, what I'm saying is 2 raised up to what power equals 32? 2 raised up to the 5th power equals 32. So you can set it up, a bunch of the different ways that we've already set these up, but that's the way you can read it in your head. 2 raised up to what power equals 32? The answer is 5. So this is log base 5 of 5. Log base b of b equals 1. For number 11, log base 2 of log base 3 of 81. Log base 3 of 81, 3 raised up to what power equals 81? 3 raised up to the 4th power equals 81. So this is going to be log base 2 of 4. So then you can say 2 raised up to what power equals 4? The answer is 2. And last one, log of ln of e. Ln of e equals 1, because they're both base e. So this is going to be, it's going to be log of 1. That's log base 10 of 1. Any base, log base anything of 1 equals 0. Okay, so make sure you know all these properties and different ways to evaluate logs. It'll definitely come in handy. So that's it for section 4.2.